Hi, here we discuss about the project Scalable 5G NR Rate Matcher and Rate Dematcher for efficient use in FPGA accelerators. Here, modern wireless communication systems such as 5G, satellite communication, IoT networks, and high-speed data links demand efficient modulation techniques and high-throughput digital processing to meet ever-increasing performance requirements. Among various schemes, quadrature phase shift keying, or QPSK, stands out due to its simplicity, robustness, and balanced spectral efficiency, making it highly suitable for FPGA-based implementations. However, practical systems continue to face critical challenges, including limited transmission bandwidth, mismatches between high-speed digital processing and RF constraints, and inefficient hardware utilization in conventional designs. Most existing approaches tend to focus only on modulation, demodulation, or coding individually, without addressing the integration of high-speed parallel data handling with optimized hardware efficiency. In this work, a complete FPGA-based communication system is developed using 4 QPSK modulation and demodulation, incorporating an 8-bit parallel data path operating at a high system clock frequency of 500 MHz. This enables a peak digital throughput of 4 gigabits per second. Despite this high processing capability, the design reveals a practical limitation in transmission when constrained by a 27.77 MHz carrier frequency, clearly highlighting the gap between digital processing speed and actual communication bandwidth. The proposed architecture emphasizes pipeline optimization, precise synchronization, and efficient data flow management to enhance overall system performance. The key novelty of this work lies in demonstrating a high-speed parallel processing architecture integrated with QPSK communication, while also analyzing the disparity between achievable digital throughput and bandwidth-limited transmission. This provides a scalable and practical foundation for future systems, including OFDM-based architectures. The design is implemented and functionally verified using model sim simulation and further synthesized on an Arctic 7 FPGA to evaluate real hardware performance. Resource utilization is carefully analyzed in terms of lookup tables, flip-flops, delay, and power consumption, showing optimized usage with reliable operation. Overall, the results confirm that the proposed system achieves high-speed performance with efficient hardware utilization, making it a strong candidate for next-generation communication system development. Now we can verify this paper. This paper addresses the inefficiency and low scalability of existing 5G PHY implementations by proposing a high-throughput FPGA-based rate matching and rate dematching architecture. It introduces a novel memory-efficient and parallel processing design that improves hardware utilization while achieving scalable, high-speed communication performance. This figure 1 illustrates the complete transport block processing procedure in a 5G communication system, showing both the transmitter operations and the receiver operations. Starting with the transmitter side, the process begins with the formation of a transport block, which contains the user data to be transmitted. A cyclic redundancy check, or CRC, is first added to the entire transport block to enable error detection at the receiver. The transport block is then divided into smaller segments called code blocks, allowing efficient processing using LDPC coding. Each code block is further appended with its own CRC to ensure localized error checking. Next, filler bits are inserted where necessary to match the required input size of the LDPC encoder. The data then undergoes LDPC encoding, which introduces redundancy to improve reliability during transmission. After encoding, a rate matching process is performed through bit selection, where bits may be punctured or repeated depending on channel conditions and required data rate. Following this, interleaving is applied. This step rearranges the bit sequence to spread potential burst errors across multiple symbols, improving the robustness of the system. Finally, all processed code blocks are concatenated to form a continuous bit stream, which is then forwarded for QAM modulation and transmission over the channel. Now moving to the receiver side, which represents the receiver processing, the operations are essentially the reverse of the transmitter. The received signal is first demodulated to produce log likelihood ratio, or LLR values, which provide soft information about each bit. These LLR values are then deconcatenated into individual code blocks. The de-interleaving process restores the original ordering of bits by reversing the interleaving operation performed at the transmitter. Next, inverse bit selection, also known as rate dematching, reconstructs the original data sequence by combining repeated bits and compensating for punctured bits. Filler bits that were added during transmission are then removed. If retransmissions have occurred, the HARQ combining block merges multiple received versions of the data to improve decoding reliability. The processed data is then passed through the LDPC decoder, which corrects errors and recovers the original bit sequence. Each code block is checked using CRC, and then all blocks are reassembled through code block desegmentation to reconstruct the full transport block. A final CRC check is performed on the entire transport block to confirm successful reception. If the check fails, a retransmission is requested. Overall, this diagram represents a highly optimized and symmetric processing chain where the transmitter focuses on encoding, protection, and data formatting, while the receiver performs decoding, reconstruction, and error verification. This pipeline structure is well suited for FPGA implementation, enabling high throughput and parallel processing in modern communication systems. This work we have done in Verilog HDL, system verification done in ModelSim, and synthesize using Xilinx Vivado Arctic 7 FPGA. This is the Verilog HDL coding for Rate Matcher. This is the simulation report. Here you can verify the data transfer of transmitter signal. This is the Verilog HDL coding for Rate Dematcher. This is the simulation report. Here, you can verify the receiver process and recover data. This process done with 8-bit data rate, throughput done with 4 gigabit per second, bit rate done with 55.54 megabit per second. This work synthesis report done with Arctic 7 FPGA. This is the synthesis report. This is the RTL schematic for transmitter. This is the RTL schematic for receiver. And we have written an abstract document for this work. Title, Base Paper Abstract, Objective of this work, Proposed Title, Proposed Abstract, Existing System, Disadvantages, Proposed System and Related Notes, Literature Survey and References. Thank you.
Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join Nxfee Innovation, shaping your future for VLSI research. Are you planning to publish your next innovative research in IEEE Transactions on VLSI 2025? Welcome to Nxfee Innovation, where future-ready VLSI research projects are designed with novelty and quality for global researchers. At Nxfee, we provide novelty-based VLSI projects carefully aligned with IEEE Transactions on VLSI 2025. These projects are not yet published, offering you a clear opportunity for unique contributions in top-tier journals. Our research covers key domains like low-power VLSI design, analog integrated circuits, FPGA implementation, signal processing architectures, and emerging applications such as cryogenic front-end ASICs, physical unclonable functions, and self-recycling SRAM cells. Each project comes with a verified novelty, simulation results, and complete customization for your journal publication. You'll find practical design files, HDL codes, schematics, and step-by-step explanations to guide your research journey. We provide 100% accurate results and comparisons of source code with all results, basic documentation, and explanation video. We provide execution support with explanation-recorded video explanations on your system. IEEE guidance for paper writing and journal publication. Affordable project packages with ongoing support. Customization to match your research needs. Early bird offers and discounts for researchers. Don't miss the chance to publish in IEEE Transactions on VLSI 2025. Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join Nxfee Innovation, shaping your future for VLSI research.